Please join me one more time in giving a round of applause for Pete Gorojec and this outstanding panel. I learned a lot from this outstanding panel. I hope you did as well. Our next session highlights two leaders driving mobility innovation across the University of Michigan. Bogdan Epureanu is a professor of mechanical engineering and the director of the Automotive Research Center, a US Army-funded collaborative research partnership. His work focused on advanced modeling and simulation to support future vehicle technologies across ground, air, and maritime systems. Harry Liu is a leading expert in cyber physical transportation systems, specializing in smart traffic signals, connected and automated vehicles, and AI-driven mobility solutions. As director of the University of Michigan Transportation Research Institute, he leads interdisciplinary research advancing the safe and efficient deployment of next-generation transportation technologies. Liu also directs the U.S. Department of Transportation's Center for Connected and Automated Transportation and the Michigan Traffic Lab, and is a professor of civil and environmental engineering at the University of Michigan. He holds a PhD in civil and environmental engineering from University of Wisconsin-Madison. Together, they will share how University of Michigan is helping to shape the future of mobility across research, education, partnership, and workforce development in our nation. Please join me in welcoming Professor Bogdan Epureanu to the stage.
Thank you very much for the very kind introduction. Let me see where the clicker is. So, and thank you very much to all of you for participating in this brilliant event focused on mobility. I'm here today to tell you how the University of Michigan is thinking about reimagining the future of transportation by creating this organization that we call Mobility at Michigan. But let me start by saying first that what is most important is to understand that we live in a time of unprecedented opportunities, but also they come at the same time with very significant and very urgent challenges for mobility. In particular, the opportunities are created by the fact that technological development is advancing at the fastest pace as ever, as it was also discussed in the previous panel. And this technological innovation at faster pace needs to be adopted, needs to be implemented together with to address the current changes in customer behaviors to adapt to the new transportation patterns that are emerging. And also these new advanced technologies, the combination, for example, autonomy and AI for vehicle technologies are able now to address new areas of the economy, whether it is planetary exploration, whether it's agriculture, mining, disaster relief operations, and many others. But to do all these things, to make these opportunities a reality, we also need to address very important challenges. Safety, for example, remains a very important challenge. Injuries on U.S. roads remain excessively high, despite a lot of new technologies being introduced on vehicles. Also, the transportation industry is the largest single source of U.S. carbon emissions. And on a different perspective, activities of U.S. adversaries pose threats to national security as well as to supply chains. So we need to address these challenges by reimagining transportation, reimagining mobility of the future. And the University of Michigan is fantastically positioned to address that because we have a very strong foundation. And the foundation is not just because we have large amounts of dollars, over $600 million investments in transportation and mobility research, but but also because we have the human capital to drive this innovation with over 120 faculty members that are dedicated to research in mobility, and as well as an entrepreneurial spirit with startups spinning off of the University of Michigan over the past few years. So what is the U of M solution that we are pursuing is to accelerate mobility innovation. And how we're going to do that is by integrating transportation mobility expertise that we have across the campus and beyond in order to really revolutionize the path forward in order to reimagine the future of transportation. So our goals are very clear. We have three very clear goals. First, we want to facilitate an integrated solution. And that is because the challenges that we see in mobility are very complex. We need to address them from psychology to mathematics to digital engineering and many other aspects in order to build a future that is safe, secure, and resilient. A second goal that we have is to cultivate an ecosystem of innovation, to break down silos between different domains, because it's only by breaking down these silos that we'll be able to have comprehensive solutions. And these silos are also broken down at the University of Michigan by integrating research, integrating educational programs, workforce development, and public engagement. A third goal that we have for mobility at Michigan is to accelerate the thoughtful advancement of these technologies. And that is because advancements in one technological domain might have unintended and perhaps undesirable consequences in other domains. So we need to have a comprehensive view in areas of autonomy, electrification, low carbon fuels, connectivity, and digital engineering in general. So with these three goals in mind, we started the organization, the Mobility at Michigan, by integrating the expertise that we have, integrating facilities, and focusing on real-world validation. And there are 5 organizations that are participating in this. The Automotive Research Center, or the ARC, that focuses on off-road mobility or off-road autonomy, digital engineering, and teaming between autonomous vehicles and humans. Of course, and I'm going to discuss more about that in a minute. Of course, the Electric Vehicle Center that you're all learning about today, that is focused on a lot of things from electric drivetrains to batteries, grid integration, and so on. But we also have the M-City that is focused on urban autonomy, data, and safety that Professor Liu is going to talk about later, as well as UMTRI, which concentrates on human factors infrastructure. We also have the Lay Automotive Lab, which focuses on powertrain systems and fuel technologies, in particular with its 19 test cells for developing new powertrain systems, new fuels, and now new developments in the area of batteries and grid integration. But I would like to focus primarily for today on the ARC, the Automotive Research Center. And what is the ARC? It's the preeminent research organization of the United States Army, and in particular, Army Futures Command, in the area of modeling, simulation, more broadly, digital engineering of autonomous ground systems. And we work with both physical testing as well as synthetic environments, deploying digital engineering technology, developing and deploying new digital engineering technologies in a combined fashion. Our particular mission is to advance off-road mobility and mobility and operations with of heterogeneous teams that include both humans and vehicles. And these vehicles are autonomous and adaptable. And this is a very complex, very interdisciplinary problem, because we are studying everything from the interaction of grain of sand in a sandy soil, how those interact with tires to provide traction on various mobility systems, all the way to how to manage fleets of hundreds of vehicles that are autonomous and they need to self-organize in order to collaboratively address very complex demands. They might be military, or they might be disaster relief operations, or mining, or other kind of things. So to address this, we need to have teams that are addressing multi-physics problems and address a very broad spectrum of scales, address a very challenging multi-scale issue. And we do that by organizing in 5 groups of technological domains that we are focusing on. And these domains are all dual use in the sense that we address the needs that our government, our military requires, but we also address them in a way that helps commercial applications. So for example, if we are focusing on vehicle autonomy, it's one of our first area that I want you to discuss, whether we talk about high-speed navigation on soft soils or resilient autonomous mobility or being able to have adaptive sensing systems, they might be used for military applications, but they're also useful for commercial applications. For example, mining is shown on the slide there. A second area is, so we don't focus just on how to make vehicles autonomous, but we also work on understanding how to think of the next generation of autonomous vehicles that are interacting with humans. We think of the vehicle not just as a device that the human tells what to do, but rather as a teammate that collaboratively works together with the vehicle, together with the human to achieve a complex goal. So therefore, human autonomy teaming is a very important aspect of our work that has clear implications in the military, but also in commercial applications such as, for example, smart agriculture, collaborative farming, and so on. In this area, we're trying to make machines, we're trying to make vehicles have empathy towards the human that they're interacting with, not just in the sense of being able to anticipate the human needs and the human intent, but also in order to do it by understanding the human state at that time. So we're monitoring cognitive loads on the human, we're working with algorithms to estimate the emotional state of the human, and so forth, in order to provide a lot of capabilities, including improved situational awareness, to mention just one. A third area, so we talked about vehicle, we talked about interaction of vehicles with human. The third one is how do we make the vehicles? How do we actually manufacture the vehicles? What are the advanced materials and structures that are needed to achieve that? In particular, in this area, I'm concentrating on bringing intelligence to the material, making vehicles more adaptive in order to be able to operate in uncertain environments in a disaster relief operation or a military operation, but also materials that provide unique attributes, unique capabilities to the system, for example, thermal camouflage or other enhanced structural properties that could be used in both military and commercial applications such as aerospace smart structures. A fourth area is intelligent power systems. And the reason why we focus on this is because once you take the human out of the vehicle, when the vehicle is operating without the human inside, a lot of the constraints that are coming because of the presence of the human in the vehicle, on the vehicle design, disappear. And then the question becomes, what are the next, the bottlenecks in the design, the next significant constraints? And power and energy is one of them. So what we are focusing on is developing intelligent power systems. They use multiple energy sources. They're omnivorous in terms of exploiting the energy surrounding the vehicle. They can adapt the energy management process. They can learn, powertrains, they can learn how to do better optimize energy use, especially during operations, whether that is a hybrid tactical power system or it is an AV powertrain application in commercial. And the fifth and last area that I wanted to discuss is that of system of systems. We need to be able to integrate all these domains that I mentioned, and a system of system is necessary for that in order to understand how we'll operate large fleets of vehicles that do that. A fleet level autonomy is necessary. When you imagine 5, 10 people that are working with 100 autonomous vehicles simultaneously achieving a very complex task, that requires new technology, new AI-based methodology for multi-agent cooperation, collective intelligence approaches, and so on. They have implication not just for the military, for example, on defense networks, integrated defense networks, but also to commercial applications such as intelligent, smart energy integration technology. We do this, all these things, by also building capabilities, in particular focused on an environment that is interactive, immersive environment for allowing the interaction of humans with these machines in simulation through digital engineering to address the big challenge of off-road autonomy. And we do this through a variety of tools. I'm only mentioning here a few: the high-fidelity off-road simulations, off-road navigation that we do both in physical testing and in digital, automatic or autonomous detection of edge cases for adversarial scene generation, or sensor validation. If you apply digital engineering methodologies, you have digital sensors. How do you know if two different digital sensor models are equally good, or which one is better in which condition, or whether the accuracy of those models is good compared to actual physical data? These kind of algorithms help in general with real to SIM transference, and including scene reconstruction algorithms that we are using. We are a partnership that involves, our sponsor is the Army, as I mentioned, in particular the Ground Vehicle Systems Center that is located at Detroit Arsenal in Warren, Michigan. We also, I would like to highlight here that we are a convergent team. We bring in expertise from very many different domains to focus on specific challenges. Whether we bring in psychologists or mechanical engineers or computer scientists or aerospace engineers or experts in information science, they come together to solve significant challenges for the US government and for our industry partners. All our projects have what we call a quad structure. We explicitly identify the stakeholders, the faculty, the students, as well as the government agencies that are involved in every single one of our projects, and the industry partners that are involved in every single one of our projects. So this squad structure allows us to ensure that the 37 projects that we're running today will have a pathway to transition, both to solve government challenges and to industry. So with that, I would like to actually extend an invitation to you to join our collaborative vision. I put there a link if you'd like to contact us. Of course, help us define a vision for transportation in the future. Join Mobility at Michigan. And also, I wanted to extend to you an invitation to another event where you can learn much more about the ARC, which is on June 17, 18. It's our annual review, very much similar to this event. And also to visit our booth where you can explore some of the techniques that we're using for understanding how to drive autonomous vehicles on soft soils in very challenging 3D terrains, or how to use digital engineering in synthetic environments to understand cognitive workloads on the humans and things like that. So with that, I hope that you are equally enthusiastic as we are at the University of Michigan in reimagining the future of transportation. And please join us in Mobility at Michigan.